So yeah, thank you so much for coming to my talk in this Analogical Mind seminar. In general, as Margarita said, my research is on children's and adults' mathematical thinking and learning. Like many of you, I'm interested in analogies and I'm interested in math instruction. In particular, I'm really interested in how students use what they already know to learn about new and more difficult concepts. And you all may know that analogies are really common in classroom instruction. So for example, in a science lesson, if students are learning about the structure of an atom, a teacher might help students understand the structure really rapidly by making a connection to a much more familiar concept for which the structure is already known. So perhaps the structure of a solar system, which also has a component in the center and sort of other components in orbit. So it's not unusual for teachers to draw such analogies from children's more familiar prior knowledge to help structure their learning of this new topic. I think analogies are particularly helpful in math. Before everybody came in the room, Matthew and I were sort of talking about how I kind of think analogies are like obligatory in math because later concepts almost always build on something that kids already know and extend something they already know. So for example, Thompson and Upfer and their colleagues have shown that elementary age children can learn to understand the relative magnitudes of larger numbers and fractions by drawing on their understanding of magnitudes of more familiar, smaller whole numbers. A lot of my work has focused on children's fraction learning, and one particularly difficult concept for children to understand is what it means to divide by a fraction. We sometimes measure this by asking children to draw problems like 6 divided by 1/2 on a diagram like this one. I'm going to show you today that children can learn this really rapidly by making an analogy to whole number division. So if we can understand whole number division as how many times the second number fits into the first number, it's a lot easier to grasp the idea that dividing by a fraction is also finding how many times the second number fits into the first one. So in this way, making an analogy between something that's really familiar to, say, a 6th grader can help them learn something new really rapidly. So as I said in math, I think there are lots of examples of later learned concepts that directly support concepts or are directly supported by concepts that are learned earlier in mathematics. Here in the US, our national standards also often explicitly state that teachers should make these types of links during instruction. For example, in this example, stating that students should be able to use their prior knowledge of division in order to engage with fraction division. And furthermore, empirical research shows us that teachers do very often try to draw analogies during mathematics instruction. So I want to take a second to sort of summarize where we are and talk about where we're going today. So I've been talking about how analogies are common and potentially a really useful tool for helping children use what they know to learn mathematics. And the key question of my talk today is how can we best leverage students' familiar prior knowledge during new learning? And I'm going to argue that we don't actually know the best ways of making use of what children know in the classroom. And there are a lot of open empirical questions. Of course, this question about leveraging prior knowledge is critically an issue of transfer. So when we ask children to draw on their prior knowledge or experience while learning something new, we're asking them to transfer their knowledge. And in analogy, as I'm sure you all know, we call these the source of transfer and the target of transfer. And there's of course a lot of research in cognitive and developmental science on transfer. But a lot of the research has focused on how to teach today in a way that's going to transfer to the future. So in other words, what are the learning conditions for today's instruction that will be most likely to result in transfer to some new untrained problems or new untrained contexts? So for example, a lot of studies of children's learning sort of focus on developing some experimental instruction today that's going to be most likely to transfer to something the child has to do later. So maybe it's an immediate post-test, maybe it's a delayed post-test, maybe it's standardized achievement test many days later. And many researchers suggest that for such transfer to occur, you need a sufficiently abstract, portable mental representation of those source problems to transfer or generalize to the target problems. And there are what I think some really clear findings about what features of today's instruction can help children to develop that abstract mental representation that would transfer. So for example, comparing multiple examples of a source problem can help kids develop deep conceptual understanding that transfers to new problems. Teachers can also use concreteness fading, where earlier examples are more concrete and later examples are more abstract. It also just occurred to me that many of you who are here today have done this research, so thank you. And then also in mathematics, we know that when comparing examples, it's helpful to use language that helps children focus on the relationships that are shared across all the examples. And then, and particularly in math, we know that certain types of visual representations like number lines can really help children develop numeric understanding that then transfers to other contexts. So again, this is all important research done by many of you who are here today. And I think it is important, but I'd like to propose that this research doesn't tell us enough about how we might engage in analogical transfer in the classroom. So imagine that I'm a sixth grade teacher and I'm talking about fraction division today, and I want my students to learn really well, and I want to help them draw on their prior knowledge of whole number division. So that means that today's topic is not the source of analogical transfer. Instead, it's the target of transfer. And the source of our analogies in the past, sometimes many years in the past. So instead of asking a question of how do we teach today to help children develop deep conceptual knowledge that's abstract enough to transfer to something tomorrow, I want to ask during today's lesson, how do we invite analogical transfer from the past? Children have so much prior knowledge, but I don't think we quite know enough about how to leverage it. And so in contrast to intervening on the source of transfer, the work that I'm going to show you today intervenes on the target of transfer in order to sort of bring that knowledge in from the past. So this brings me back to my question of how do we best leverage students' prior knowledge during new learning? So next, I'd like to introduce two contrasting ways of supporting children's analogy making in mathematics. So one way is to provide explicit support for the analogy, which is probably most people's intuition for what we should do. So I'll talk about what that is and the research that supports it first. And then I'm going to introduce you to the idea of implicit support for analogy, which is an idea that I've been exploring in my own research on analogy for a number of years now. So I'm going to talk a little bit about the classic view of analogy and problem solving. I'm sure this is old hat to most of you, but I still think it's helpful for you to see how I'm thinking about it. And I'm also happy to have your comments at the end about whether you think I should be thinking about it differently. So in a classic view of analogy, transfer is rare and learners need a lot of support. So to illustrate some challenges of analogical transfer, I want to talk about one classic study from Gick and Holyoke that I'm sure most of you are familiar with. So in this study, college students became familiar with the problem in which an invading army needed to storm a castle, but the total weight of their forces will set off landmines beneath the road. So college students learn that in order to storm the castle, the army needs to split its forces, and then they have enough combined force to take the castle, but each component force is not so heavy that it triggers the mines. So then the experimenters gave the students another problem about radiation therapy. And in this problem, a patient needs radiation therapy to treat a tumor, but at full strength, the radiation will also kill the healthy tissue on its way to the tumor. So as it turns out, the solution to this problem is to split the radiation into smaller doses. That's not going to kill the healthy tissue on the way to the tumor, just like the general had to split its forces in order to invade the castle without also blowing up the mines along the way. So participants who learned about the castle problem were likely to apply a similar solution procedure to the radiation problem, even though the problems appear very different. And so according to the classic literature on analogical problem solving, a few things need to happen for adults to successfully apply that familiar or sort of more familiar knowledge to the new problem. It's also worth noting that in the study, the familiar knowledge was also just learned. So it's not really reaching back into the past in the way that I just talked about it. So in order for this to occur, first the adult needs to realize that the conceptual structure or the relationship between elements of the castle problem is identical to the conceptual structure of the radiation problem. And in doing so, they need to sort of figure out which elements correspond to each other. So in this case, realizing that the army is like the radiation and the castle is like the tumor. And then finally, the adult needs to figure out how to adapt the strategy of breaking up the army to the radiation problem and realize that the beam can also be broken up into smaller doses. So as I'm sure many of you know, there is a lot of research on these three processes. So identifying when you have a helpful prior knowledge, mapping across corresponding elements, and also adapting the strategy. So in mathematics, analogy can be difficult for children because students might have difficulty identifying a helpful analogy. Students have multiple competitors in their prior knowledge, and that might mean that it's hard to decide which analogy is going to be most useful. For example, by the time children learn about fraction division, they have knowledge of a lot of other kinds of fraction problems. Some of these problems share the same underlying conceptual structure or relationship between elements. Other familiar problems like fraction subtraction, for example, they have a different conceptual structure since subtraction is not analogous to division, but sometimes these problems are perceptually similar. They have similar perceptual objects like the representation of quantity as a fraction. They might have similar labels, like we might call these both fraction problems. And novices are often drawn to these similarities and may be likely to draw on their knowledge of perceptually similar problems rather than necessarily thinking about conceptually similar problems. And certainly in children's fraction learning, we do see that a lot of the errors that they make indicate that kind of transfer from these other fraction problems. Also, recency likely matters. So children may be more likely to transfer strategies that were very recently learned. And this can be problematic in mathematics because sometimes the topics that are most conceptually relevant are not very recent. By the time children start learning about fraction division in 5th or 6th grade, they had learned about simple whole number division several years earlier. On the other hand, sometimes very recently learned or recently practiced problems don't make a great analogy. When children are learning about fraction division, they've usually just learned about other arithmetic operations with fractions like subtraction and multiplication. And although subtraction and multiplication are related to division, these problems don't have the same conceptual structure. So the analogy might not be all that productive. Finally, mapping across similar elements in an analogy and adapting strategies to new situations is effortful. Novices don't always know which familiar elements correspond to which new elements, and novices sometimes make errors when trying to figure out how to adapt a familiar structure to a new situation. So in this view of analogical transfer, if we've got three processes to guide, then the best way of helping students make analogies is to provide explicit support for each process. So based on prior research and also a cross-cultural study of teachers' actual behaviors when introducing analogies in the classroom, Richland and her colleagues have suggested a number of explicit cognitive supports for analogy. Now, the first two, I think, are important really for any type of analogical instruction, and that's to use a source that is really familiar to students. You can't leverage students' prior knowledge if they don't have sufficient prior knowledge, so you have to use a familiar source. The second that I'm going to actually provide some data for later in the talk is the presence that the presence of a visual representation is helpful. That was a hypothesis that they made. So I agree with Richland and her colleagues that any type of analogical instruction should probably include these features. On top of that, Richland and colleagues have argued that to fully support identification, mapping, and adaptation, teachers should keep that source problem visible during target instruction. They should align the visual representations in space, and they should use gesture to highlight the corresponding elements. So, Richland and her colleagues have really nicely argued that this type of direct, explicit instruction on analogy is necessary in some cases because without it, engaging in analogical reasoning really can tax working memory. And when that happens, learning might be unlikely to occur. So I'd like to acknowledge that their account is supported by a lot of data. I just want to argue that sometimes, in some cases, the cognitive supports might actually increase the cognitive load of learning from the analogy, and maybe unnecessarily so in some cases. I think it could have a large high cognitive load because of how many things there are to pay attention to when you make explicit analogies. So when we do this explicit support, you're asking the learner to pay attention to the familiar representation and also all the links between the familiar representation and the new representation, while they're also trying to learn something new and challenging. And it just might be a really overwhelming amount of information to process, particularly for younger learners. So next, I want to argue that instead of explicitly directing learners' attention to an analogy between something they know and something they're learning, that it might be possible to support learning through a more implicit analogy, in which recently activated knowledge can affect the interpretation of new learning without a lot of explicit mapping and adaptation. Okay, so why might I think that we can support analogical transfer in this more implicit way? So first, I'd like to consider research with young children that suggests that transfer isn't so hard won under some cases. So for example, Chen and his colleagues had parents show their babies how to solve this problem, where the infant is sitting in front of a toy, but she has to remove a barrier, and then she has to choose the right cloth that's attached to the toy and pull it toward her. So they found that infants were really good at using this strategy on later problems that had different elements, but the same structure, the same relationship between elements. And that suggests that this research suggests that young children can learn by making analogies to their familiar prior knowledge, perhaps without a lot of conscious effort to identify, map, and adapt the original strategy, but probably recency is playing a big role here. There's also research with adults showing that they do engage in spontaneous transfer from source problems to conceptually similar target problems, and sometimes without any conscious awareness of the analogy. Instead, adult learners' prior knowledge guides their interpretation of new situations by affecting how they perceive and thus interpret those new situations. So for example, in one study by Day and Goldstone, adults were first taught about a physical system in which they had to control the location of a ball that's oscillating between two pins by using a fan. And then they solved a problem where they had to control the size of a population by using media advertisements. And many adults demonstrated analogical transfer from the first scenario to the second, despite a lot of differences in the surface features. More importantly, for my talk and my argument today, some of the adults in the study showed evidence of analogical transfer without being consciously aware of any similarities between the old problem and the new problem. Similarly, Shen and Dunbar found that adults learn from an analogy between viruses and a problem about viruses and a problem about genetics. But again, many of the adults were not consciously aware of similarities, and their conscious awareness in the study did not moderate the effects of analogy. So it wasn't necessary for adults to even know that an analogy was possible for the analogy to be useful for them. So in contrast to explicit support for analogy, I propose that under some conditions, we may be able to implicitly support children's analogical transfer during new instruction by simply activating prior knowledge of a relevant mathematical relationship immediately before target instruction or target problems. There's my activate prior knowledge immediately before. And I'd like to show you what this looks like by sharing some evidence from 3 studies. The first study is about problem solving. The second study is activating before a learning situation. And then the third study compares implicit support to explicit support directly. So in study one, we measured children's conceptual understanding of fraction arithmetic by asking them to demonstrate problems using these physical manipulatives. So kids were given these fraction bars that can be split into different fractions like halves and thirds and fourths. So for example, on this trial, the child is being asked to demonstrate 8 divided by 3/4, and she's showing us 8 blocks that she's then going to break into 3/4 pieces. So for each problem, I coded children's strategies for the conceptual structure that strategy reflected. So the study included some 5th and 6th grade children, and the kids did 8 sets of problems with 4 problems in each set. There were 2 experimental conditions, but in both experimental conditions, kids did fraction division last. Also in both conditions, kids solved a whole bunch of other whole number and fraction arithmetic problems in the first 7 sets. So here in the condition I'm showing you, they did whole number addition and then fraction addition, whole number subtraction, then fraction subtraction, whole number multiplication, fraction multiplication, and then whole number division and then fraction division. So critically, half of the students did whole number division immediately before solving fraction division problems. And remember that they have the same conceptual structure, and so we might be setting up a really good analogy here. So in this condition, you can see the problems are blocked by operation, and in the other condition, the problems were blocked by number type. So they did all the whole number operations first, and then all the fraction operations. So in this condition, the most recently activated knowledge was actually fraction multiplication. And fraction multiplication, again, is related to division, but they don't have exactly the same underlying structure, and you don't need the exact same strategies for those. And you can see we still had kids practice with whole number division, but it was several minutes earlier with a lot of intervening problems. Okay, so I'm going to show you how many fraction division problems kids modeled correctly out of 4 total fraction division problems. And we found that, as expected, children who had been solving whole number division really recently were significantly more successful in demonstrating the conceptual structure of fraction division. So that tells us that activating children's conceptually similar familiar knowledge of whole number division helped them to better understand fraction division, and we didn't even give any direct instruction, but instead recency really matters here. Okay, so in the second experiment, we gave children a lesson. We actually gave instruction about fraction division. This lesson was couched in a story about the Acme Construction Company. They're building a new road. The road will be 6 miles long. The builders can build half a mile a day. So how many days will it take to build all 6 miles? We taught them about how to represent this with a symbolic equation. And then we taught them about invert and multiply. So the lesson was about 10 to 15 minutes long, but before the lesson, we manipulated what kind of analogy children would make by having some kids solve warm-up problems by having kids solve different types of warm-up problems. So half of the kids warmed up with whole number division, and again, this should be helpful. And then the other half of the children warmed up with other fraction arithmetic problems like fraction subtraction and fraction addition. So this effectively sets up that analogy that's not as helpful. Okay, so remember, some kids warmed up with whole number division, some kids warmed up with addition and subtraction, and then we also manipulated whether we asked them to explicitly link between the warm-up problems and the lesson. So some were asked to link and some were not asked to link. So for half of the kids, they did their warm-up problems, and then we kept the warm-up problems out during the lesson. And at several points during the lesson, we said, you know, do you think this is related to the warm-up problems, and how is it related? How is it similar to the warm-up problems you did? And then the other half of the kids were not asked to link at all. After they solved the warm-up problems, we just put them away. And we never talked about any possible connections between the warm-up problems and fraction division. Okay, so we had, again, 5th and 6th graders. Now, these 5th and 6th graders had some instruction on fraction division, but kids had actually very little procedural and conceptual knowledge coming in. What we often see is that some kids do know how to invert and multiply, but many don't know how to sort of represent the conceptual structure of fraction division. We did exclude a handful of children who were at ceiling here, but most kids didn't have really any knowledge of fraction division. So the kids came to the lab, they did a pre-test, then they did the warm-up problems, then we did the lesson. It was about dividing by, so warm-up problems, either division or other operations, and then the lesson with the linking or without the linking, and then the post-test. We measured conceptual understanding at the beginning and at the end. We used a sort of story generation measure that had been used before, and a diagram drawing measure that we've continued to use since then. Okay, so here you're seeing different scores on the y-axis, and I'm going to show you the effect of different warm-up problems in the implicit condition first. So the where they're warming up but not linking. Okay, so when kids were just warming up but not asked to link, so we're activating their relevant knowledge, but we're not giving it that explicit support for linking, we can see that kids learn a lot better from the lesson if they had been warming up with whole number division than other operations on fractions, which is sort of in line with this idea that activating knowledge can support analogical transfer. I'm going to show you the results from the explicit condition. So unexpectedly, kids did sort of equally poorly, regardless of what kind of warm up they did when we asked them to do that explicit linking. You can see actually that kids who were asked to make explicit connections to whole number division hardly learned at all. And so you might be wondering, like, what's that about? So I'm going to tell you a little bit about how I interpret this finding. Okay, so why was drawing attention to what should have been a good analogy worse for kids learning than not drawing any attention to it at all? Why? Well, one reason is that, I asked the kids to think about how similar they were and what parts were similar to each other. So the identification of the analogy is explicit. I gave them the whole number division warm-up problems, but I didn't actually provide a whole lot of support for mapping and adapting. Instead, any mapping and adapting that happened was likely child-driven. And when children are given opportunities to make analogies, they don't always make the right connections. Research from others suggests that without providing any support for the analogy, we might actually be inviting unintended connections. So to examine whether kids were trying to make analogies in this condition, but making those unintended connections, we looked closely at what kids wrote in their story problems at post-test, which was one of our measures of conceptual understanding. And sure enough, we did see some evidence that kids were trying to transfer, actively trying to transfer what they knew about whole number division to fraction division. So that it does suggest they were explicitly making the analogy. Their story problems reflected ideas like sharing or that the answer should be smaller than the first operand. So these are really common components of children's understanding of whole number division, but these ideas about whole number division don't necessarily help them to think about what it means to divide by a fraction. Smaller. So, these errors show us that mapping and adapting are really hard. And it may have been that, if we had shown students how to map the analogy, that might have been much better than what we did in the study. Okay, so what I've shown you, I've been arguing that we can help students learn from implicit analogy. In both of these studies, I have used a more child-driven analogy, so it's kind of up to the child to draw the right analogy. But we might wonder, well, what about teacher-driven analogies? So maybe when the teacher is making the analogy and the teacher helps the child make the right connection and supports their mapping and adaptation of that familiar knowledge, this might be as good or even better than implicit analogy. So we tested that hypothesis with a direct comparison. So in this study, we had 3 experimental conditions. We had a no analogy condition, an implicit analogy condition, and an explicit analogy condition. I'm going to show you the implicit and explicit conditions first. So in both conditions, children were first reminded about whole number division using 2 problems. So the teacher showed them how to think about division as making groups as big as the second number that fit in the first. And then the teacher demonstrated 2 fraction division problems in the same way using similar language and similar diagrams. But just like before in the implicit condition, once the teacher was done talking about whole number division, she never referred to it again. Those problems went away and she didn't talk about it again. In the explicit analogy condition, though, each time the teacher introduced a new fraction division problem, there was a similar whole number division problem present, and the teacher talked about the connections between them. So I've been showing you some of these images throughout the talk, and the images of the teacher making connection are all stills from the explicit condition of the study. Okay, so to summarize, kids in all three conditions got a short lesson on fraction division. In the analogy conditions, they did whole number divisions first. In the implicit analogy condition, when they introduced fraction division, there were no whole number division problems present. In the explicit analogy condition, we implemented all of those explicit supports for analogy that have been recommended by Richland and colleagues. And then in the no analogy condition, it was a lot like the implicit analogy condition, except that during the whole number division part at the beginning of the lesson, we just had extra examples of fraction division. So that helped us control for the length of the lesson. And it's a pretty strong control because they're getting actually twice as much instruction and twice as many examples of fraction division as in the analogy conditions. Okay, so here we just had sixth grade students. Again, these students very often know procedures, so they kind of know invert and multiply, and sometimes they can do it correctly and sometimes they don't, but they don't usually have knowledge of the conceptual structure. So they had a pre-test, and then they got their video lesson, and then they had a post-test. Okay, so I'm going to show you their conceptual knowledge at post-test, controlling for pre-test. The analogy conditions are on the x-axis. And sure enough, we found that children in the implicit analogy condition learned more than either those who saw no analogy at all, or even those who saw this explicit teacher-directed analogy that included all these explicit supports for analogy. Also, seeing the instructional analogy with explicit supports was no better than seeing no analogy at all. Okay, so I've shown you that in an implicit analogy, when we activate children's relevant prior knowledge with a warm-up activity, this results in better learning than no analogy at all. Also then an explicitly supported analogy that's more child-driven, and an explicitly supported analogy that is teacher-driven. And of course, because you're all amazing scientists, you're probably wondering, what do I think is the mechanism of this effect? So I'm going to tell you a little bit about what I think. So I think that when we reminded students about whole number division, but then didn't draw attention to the analogy, they still are learning. And so along with the evidence I presented earlier in the talk from adults and from young children, I think this could be converging evidence that analogy can occur through what Leach and colleagues have called relational priming. The way I think about it is that when we ask children to remember and practice whole number division concepts, this serves to activate their understanding of those division relationships. And then, of course, this mental representation continues to be active even when the kid's no longer working on that problem. But that when they're invited to think about fraction division, this recently activated familiar representation then sort of shapes how children interpret and construe that incoming problem. Leach and colleagues have proposed that this is a more developmentally appropriate mechanism for explaining how kids make analogies compared to other models of analogy that may be based largely on the adult literature. So this relational priming is also what I think probably is underlying the spontaneous analogical transfer that we see in infancy. And remember that infants can spontaneously transfer across analogical problems, but recency matters a lot. I also want to acknowledge that I realize this is a little bit of a controversial view, but we have been working on testing this hypothesis in our lab. Okay, so how can we teach today in a way that invites transfer from the past? So I think a structured warm-up assignment that uses visual representations, that's well aligned with the relationships that are in today's topics, can help students to learn better from the direct instruction that the teacher is going to give on today's topic. Okay, so I told you that there were lots of open questions, and I want to share some of those with you. So one open question is the role of these visual representations in transfer. And throughout the talk, I've shown you at least 2 ways that we can represent fraction problems. We represent them with circles. I also represented them with number lines. And these can be, visual representations can be very helpful because they can help students understand conceptual relationships in math and science very quickly. But different kinds of diagrams have different affordances for representing mathematical relationships as spatial relationships. When looking at kids' fraction learning, we know that there's a number line advantage for learning about the magnitudes of fractions, such that when kids learn on a number line-like representation, they're more likely to make more accurate comparisons when the visual representations are gone, as compared to kids who learn on those circle representations. In my own prior work with kids, I've shown that children are also better able to represent the conceptual structure of fraction division when they're asked to do so on a number line as compared to circles or no visual representation at all. So given that we know from prior research that number line representations support whole number magnitude understanding, and they support fraction magnitude understanding and fraction division understanding, I wondered whether number line representations might actually better support transfer from whole number to fraction concepts. So in this study, it's with undergraduate adults, it's not with children, but they were randomly assigned to demonstrate fraction problems in one of 3 visual representation conditions. There was a symbol-only condition where participants were asked to solve problems, but there was no visual representation present. There was a circle condition in which participants were asked to use circles, and then finally a number line condition. So this method was really similar to what we had done with kids, but it also included manipulating the warm-up as well. So some participants, they warmed up with whole number division, as in the other 3 studies that I showed you today, but then others warmed up with fraction addition. So I'm showing you the warm-up problem for the whole number division condition and for the fraction, for the circle condition, whole number division and then fraction addition. So you can see these are really simple problems that we're giving to adults. Like the whole number division is just 6 divided by 2, and then fraction addition is just 6 divided by 1/2. So this is really familiar prior knowledge. And then some students didn't have any warm-up example at all. So it's a 3x3 design, 3 visual representation conditions, and 3 warm-up conditions. So that means it's a little complex, but I'm going to do my best to break it down. So I'm showing you diagram condition on the x-axis. So you've got no diagram, then circles, then number lines. And then within each diagram condition, I'm going to show you the effective warm-up. So the white bar is going to be no warm-up at all, no analogy at all. The gray bar is going to be the fraction addition analogy, which shouldn't be particularly helpful. And then the whole number division warm-up, that should be really helpful. So I'm going to show you the number line data first. So sure enough, here we replicate the effect that we see in some of the other studies, that when these adults, when they warm up with really simple whole number division, they have much greater success in showing us the conceptual structure of fraction division compared to fraction addition, and also compared to no warm-up example at all. So remember, the hypothesis though is, do number lines better support transfer? So what we're looking for is that this effective transfer, the comparison between, say, whole number division and the other 2 conditions, that's a larger effect in the number line condition than in the 2 other conditions. That was the hypothesis. But you can see that the circle representation supported transfer just fine for adults. I mean, there's an overall main effect of number lines because they are helpful for representing magnitudes. But in the circle condition, we still see that warm-up effect, that when these adults warmed up with whole number division, again, they are much more successful in engaging with fraction division. And then finally, no diagram at all, we saw the adults didn't really engage in the concept at all. Even though the adults in that whole number division condition, their verbal input was identical to warming up with diagrams. They just didn't have a visual model. And so we didn't see any evidence of any type of spontaneous transfer from whole number division to fraction division there. So again, we see both a number line advantage and a warm-up advantage, but then no effect of the warm-up at all when there's no diagram, which may suggest that a visual representation may be a necessary component for this kind of implicit support for transfer. So in line with what Richland and her colleagues proposed back in 2007, I think this shows that visual representations may indeed be a critical piece of analogical instruction, but I think there's a lot of open questions about like what types of visual representations are best, and the extent to which the visual representations need to sort of match across the warm-up problems and the target problems. There are a lot of other open questions that our lab is currently working on or trying to work on as we like recover from COVID, the pandemic. Are we still recovering? I don't know. So some of the questions we're asking are, like, are learners consciously aware of drawing the analogy and the implicit analogy? That's certainly the story I'm telling you, but we have not yet measured in these studies, are they aware and whether that conscious awareness is necessary. Also interested in whether this learning from implicit analogy is moderated by working memory and executive function in the same manner that it is for explicit analogy. Of course, all the evidence I've shown you is from children's fraction learning. So we also want to explore how this implicit analogy may work in other domains. And then finally, I do think that explicit analogy is necessary in some contexts for some learners. So I think there's sort of work to be done in figuring out what those conditions are. So what are the conditions under which it's better to just warm up? And what are the conditions under which you really do need all that explicit support for analogy? Okay, so I want to conclude by making some connections to some other research that I see as related to some of the things I've shown you today. So in trying to answer this question, how can we teach today in a way that invites transfer from the past? I hope that I've shown you that implicit analogies in the form of these warm-up activities is one way to prepare students to learn from new instruction. And I think that these type of preparatory activities have a lot of promise, not just warm-up activities to invite analogy, but also Dan Schwartz contrasting cases, interventions, and concreteness fading, which some of you have worked on. I kind of see these as different types of preparatory activities, and all these activities help children to explore mathematical structure in a more familiar, less cognitively demanding context, to shape children's perception and interpretation of those more demanding or more abstract problems that come later. I think as an instructor, it's sort of relatively easy to implement a short preparatory activity or a warm-up activity to sort of get students thinking along the right track. I think the trick is actually designing the right activity, but the implementation of it shouldn't take a whole lot of time. So I think there's a lot of open questions and practical challenges to work through. And I look forward to kind of continuing this line of work and to have more answers for you in the coming years. So that is my talk today. I want to just quickly thank my collaborators, Clarissa and Martha, two fabulous people, also the many undergraduates who have helped me with these projects over the years, and the funding sources that have supported the work, and most of all the participating schools and families. So thank you. I'm ready to take questions.